So now we're going to talk about energy budgets in an ecosystem. So what we're going to start with is primary production. Primary production is going to be basically how much energy from the sun is getting converted into chemical energy for that ecosystem to live off of. So it's going to be measured in time periods. It's going to be the autotrophs that are going to do it. So most of the time, primary production is going to be using light energy to create glucose, which is then used to make ATP. There are certainly going to be other things that do chemosynthesis and some other crazy things, but the majority is going to be photosynthetic. So some crazy numbers for you. Of all the light that goes to photosynthetic organisms, only about 1% gets converted to chemical energy. That is not a lot at all. So now you can see why there's so much going into solar energy, right? If we could harness that. Now, remember we learned about the biomes and we learned about the desert and the tundra and the taiga and all those different biomes. Obviously, those are going to differ in the amount of primary production that they are going to be able to do. So what do you think would be the most productive biome from that previous chapter? Hopefully you're thinking that the tropical rainforest would be the most productive, right? So I want to show you this picture here of primary production worldwide. So there we go. There are rainforests that you can see there. So let's go over that question that I asked you. I said, which biome would contribute the most primary production per unit of area? That will be these rainforests. If I say, what biome contributes the most total primary production to the entire globe, you would hopefully say the oceans. Now I know you're probably looking at this map and going, what? The oceans are like black and purple according to this chart. That's low. However, if you think about it, look at how huge the oceans are and how much of the earth the oceans cover. So then if you look at it that way, yes, they are going to contribute the most total primary productivity. But if we say per unit of area, it's the rainforest. So hopefully you can see that difference between the two. Okay, so there are obviously going to be limits on the amount of primary production that can happen. In an aquatic ecosystem, what's going to limit primary production is going to be two things, light and nutrients. So obviously there's going to be a certain depth that light can no longer get below. Remember we talked about the photic zone. And so light, once it's not there anymore, there's no photosynthesis going on. So that's going to be the first variable that's going to have a control on primary production amounts. Then there's also going to be nutrient availability. So the two things that are going to be really limiting in the ocean are going to be nitrogen and phosphorus. Nitrogen and phosphorus are really not that easy to find. And so what's going to happen is that's going to limit how much primary production can happen. That is also the reason why if you ever got sick, seasick or anything, that's another lovely thing is yeah, Fleur the marine biologist, I get seasick. I'm so awesome. So what that means is I puked over the side of a boat a lot, and the first thing that would happen is dolphins would come up and go crazy because your vomit actually has a lot of nitrogen and phosphorus in it. So there's a lovely story for you to think about to remember that one. All right, then in terrestrial ecosystems, there's a lot more coming into play here. We're going to have precipitation, right? Water is going to be a huge one. And then also you're going to have temperature, right? So if we look at the tropics, they're obviously going to have the highest temperature and the highest amount of rain, and that's why we're going to have the highest amount of primary productivity happening there. But the second you start to get less rain and you start to get colder, you're going to have less primary production. So those are going to be the ones that are going to really limit terrestrial ecosystems. Now, another thing that we need to talk about is secondary production. And secondary production is going to be how much of those calories of food that you eat get converted into your own biomass. So how much of that energy actually stays with your body. So it's really interesting to think about, and this picture helps you to see what we're talking about. So if you look at this caterpillar, it's eating this plant material, and it's eating about 200 joules. Joules are, you can think of them like calories for what we're worried about. So half of that is going to go into feces. So half of that is coming right back out of that organism. Then 67 of that 200, that's quite a big amount, is going to be used just to keep that organism alive. then 33 of those joules are going to go into new biomass of that organism. So only these 33 joules out of those 200 are getting passed on to whatever eats that caterpillar. Okay? So basically, it depends on how well they can gain weight, right? That's kind of what we're thinking about as far as this goes. So when you hear somebody say, you know, they're on a 1,500 calorie diet or whatever, a lot of people, that's what your body requires just to maintain itself, is about 1,500 calories a day. If you eat less than that, or if you work out, then your body is going to go into the fat reserves and start to pull from that, and that's how you lose weight. On the opposite end of that, if you only need 1,500 calories a day and you're eating 2,000 calories a day, that's what causes you to gain weight, is because your body's like, oh, well, I don't want to get rid of this. I'll just store it right on your butt and make your butt fat, right? So that's how that works. So going along with that, we can call this production efficiency, the relationship between the energy that's used for growth versus the energy used for daily needs. Obviously, this is going to differ from organism to organism, right? If you think about humans, right? You've got some people who, you know, they can eat 20 Big Macs in a day and they're going to stay this thin. Whereas someone like me, if I even look at a Big Mac, I'm going to gain probably 20 pounds, right? So the way I like to look at that is that I have excellent production efficiency, and I would be an excellent addition to a food chain. That's the way I'm going to deal with it. So people that say, you know, like I gain weight easily or I have a slow metabolism, they would be excellent for the food chain because they store a lot of that energy and would pass it on to the next level. So there you go. That's how I sleep at night. Okay, so one way that we can kind of graphically represent this stuff is by using biomass pyramids and that type of thing. So this is a biomass pyramid, and what this is showing is you can see that the primary producers are going to make up the majority of this food chain, food web, whatever. And then the amount of energy that's going to make it to support primary consumers, you can see, has gone down drastically for each level, right? So the amount of primary producers is always going to be more than everybody above it in the food chain. And then the amount of primary consumers is going to be more than everybody above it on the food chain. So now maybe you can see how you run out of energy as you actually go up that food chain. And that's because we waste a lot of energy chasing after prey or keeping our bodies warm or anything like that. Okay, and so in class I'll actually no, I've got my little thing I can use here. So there's two ways that an ecosystem can look. And we can make these into pyramids as well. So what I'm doing right now, that's awful, is I'm drawing two types of pyramids that could exist in an ecosystem. All right, perfect. So here are the two types of pyramids that we can have for our ecosystems. So what I want you to think about is which one is showing more efficiency. So which one has more energy making it to that next level? Hopefully you're thinking this one. And the reason for that is because this one doesn't narrow very much from this level to this level. Whereas this one, the width has gotten much less from this level to this level. So hopefully you can see that, and hopefully that makes sense. So going along with that, this flat triangle I would say would be more indicative of like mammals and like a terrestrial ecosystem. And this one here I would say would be more like an aquatic ecosystem. So that's how you can tell the two apart. Okay. So what we're going to get into next is going to be chemical cycling, and how, so what we were talking about in this last section was going to be how energy flows through an ecosystem, and now we're going to get through chemicals cycling through an ecosystem.